Okay, so you want to, let me see. So you want the, I can log in to see. Actually, uh, I can do it here on my phone. What did you want? Oh, next Monday? So it's homework homework is 5 years? No. March 25, 10, 8 and 9. Okay. I can do that. You want to save to which day? Huh? But the following week? By Sunday next week? Yeah, okay. I'll do. It's not a big deal. I am flexible. How do you Okay, guys, let's get started. And then let me see if I got my stuff ready. So far we have talked about chapter 10 on the frequency response. Make sure I have the stuff ready. And we have talked about mostly so far we focused on the high frequency response. And we are we're gonna have a quiz today after the lecture. And I also extend the deadline for the next two homework due dates for into Sunday the next week, not this week, but the following week. So that will give you more time to work on it. Again, those homeworks are quite important, do them, get better understanding, and also help you to eventually prepare for your exams. So today we're going to cover low frequency response. And after that, I'm going to do a little bit summary and tell you a few things very interesting. What we're talking about, high frequency, low frequency, why they're different, why is the equation written different, how do we select it, and so on. If we don't have the time, maybe next week, I will go over like spending 15 minutes to summarize it. But today, hopefully, we'll cover everything. And then next week, we're going to start the next chapter. And I look at the schedule, we're pretty much okay. We might have to skip like some of the contents again in chapter 12, talk about the classes of amplifiers. We might just go, I'll give you a brief overview and so on. So that's what we have. So let's look at a little bit about when we talk about low frequency response. What we are really talking about is the high pass filter. The reason we call this a low frequency response because at high frequency, if you look at this curve, the input output as a function of input or the gain of the circuit, when output is a constant above certain frequency. So we don't care because it's a constant, it doesn't change anything, right? So what we care is about this range. In this range, our gain start to decrease, and it decreases 20 dB every decade. That when you're going to a lower frequency. Of course, when your frequency goes higher, it increases by 20 dB every decade. So you can call it decrease or increase, but most time we call this a increase, because as frequency increase, the gain increase by 20 dB per decade. It could be 40, could be 60, but in this case, it's 20 dB per decade increase. Once you get certain frequency, it's a constant. At this point, this corner point is what we call the 3 dB. 3 dB means from the peak drop 3 dB, which is 1 over square root of 2. Basically, that's what the gain drops, how much it drops. So in terms of dB, 20 log gain, it's 3 dB. So this is 3 dB. So the blue line is actual gain. The dotted line is the body plot. So that we often, when you have this one like single pole, it's easy. But when you have multiple poles, it's very easy to draw body plot instead of drawing the actual plot. The actual plot becomes very complex. So that's why body plot is good, because it really gives you the trend, but also indicate where the 3 dB is. So you know when you see the 3 dB, you know this 3 dB drop. So that's so from body plot you can sketch your actual plot. So that's easy. So in this example, what we're doing is really just getting the voltage. The frequency dependent C is on the input side, and if you get your output, if you write your output VO, you can write it as a voltage divider, which is 1 over SC divided by R plus 1 over SC times V in, right? So that's how you write the equation. And you can manipulate this equation by putting VI on this side. So we get the gain, which is equal to, if you call the voltage gain. And for that expression itself, we can multiply SC on both numerator and denominator. So we get 1 over SRC. Oh no, actually, I did it all wrong. And this becomes what? This becomes this is for the circuit that has capacitor like this. Okay, so that's for the low pass. So from here, we really get like this. So this is the low pass filter, and we write this way. So for high pass, let's write it. So we can have VO equal to R over R plus 1 over SC. VI, so AV equal to VO over VI equal to, and we can multiply again SC both numerator and the denominator. We get SRC over 1 plus SRC. And then we can divide RC on both sides, and we get S over S plus 1 over RC. So I want to challenge you at this point, one thing here. See, in the high frequency response or low pass, we write it in a different way as we write it in the low frequency response. If you look at it, here we write 1 plus SRC, but here we write S plus 1 over RC. Of course, you can multiply RC and you get 1 plus SRC, but in a frequency response, in the high frequency domain, we always write like this. We write S plus something. Like this is your omega H. So S plus omega H. But in this case, we always S plus omega L, low frequency. But in this case, we always write 1 plus S over omega H, like 1 over RC, right? So H. So why do we do that? Can anybody think about it? Why we do like why we writing in this form? Why is not the other way around? This is because of intrinsic property. So if you look at this one, if S is small, what happens? If S is small, this term can be eliminated because it's small, much less than 1. So that's why your gain is 1/1, which is 1, which is low pass. S is small, it's low pass. Well, when S is high, when S, like when this reaches 1, or J 1, and this 1 plus 1 over square root of 2, so that's your 3 dB. When this SRC is much larger than 1, you can neglect this 1. So your output is proportional to this whole term here. So you got 3 things. So when S is small, so let's see. So when S is small, or when S is equal to 1, or in this case it will be J, that's your 3 dB, or once SRC is much larger than SRC. When SRC is much larger than 1. So you have 3 possibilities. But the one of the things that's most important is when SRC is small. When it is small, that thing is gone. So the whole thing is 1/1, okay? But for this case, we have S is small, or we have S is equal to 1, or and 1/RC or something like that, or if we have once S is big. You see what happens when S is small? When S is small, which means we can neglect this, right? Because it's small. In comparison to this one, it's small. But can you neglect this one? Can you say it's small? I put it something, I don't know what else you put it. Can you? Why not? It's a small number. You can't neglect it because a small number. And then when S is small, this can be gone. So you move RC over here. So your output is really proportional to omega. See, proportional to omega, which means it's a proportional increase. You again start increase proportional to omega. When omega increase, your gain increases. Okay, that's easy to understand. So what happens when S is big? When S is big, this one can be neglected. When this is neglected, what you have? SOS is 1, which means the whole gain is equal to 1. That's why you have this constant. You see now? That's why we write it in a different way. So in the future, you see high frequency, it's always writing in the 1/1 plus S over omega H. And this is S over S plus omega H. And now, of course, there's another difference. In this one, you don't have an S in the numerator, which means there's no zeros. But in this case, you do have S. S means it's a 0. So there's a 0 on the denominator. There's a power at the bottom, okay? So that's how we really distinguish them. So now let's get down to business. Suppose you have a common source amplifier. And previously, we already know the high frequency response is because the intrinsic parameters of the device, like CGS, CGD, or CCE, CB, CBC, and so on. Okay? So those ones, they impact the frequencies, which what it means that they impact the performance of the device at a high frequency. But in circuits, we already mentioned many times, we always add some sort of capacitor in the circuit. This is actual capacitor. This is not from the device itself. This is something we added. Why do we add it? Do you still remember why we added this capacitors? What's the reason? Make a common emitter, right? At the emitter, yeah, that's how we make it. And then you say, for DC, it's an open circuit, so we can do easy DC biasing. Okay? So those are the reasons. So we always add a capacitor, but the size of the capacitor, we're going to see today, is very important. You can't randomly just choose picofarads, microfarads, whatever you want to put it there. They have to be right. Otherwise, it'll cost you too much, or it's too big, or it doesn't work very well for you. So we have to be careful. So how do we do this? Well, apparently, we can do the small signal circuit. But in this case, because we have all these things at the emitter, at high frequency, at low frequency, this is no longer open circuit. It has some impedance. So therefore, it's difficult to use a pi model because you have something in the middle. So it's easy to use a T model. Then we can do the T model. Let's do the T model. So for the T model, I want to draw it together with you guys. So we're gonna again. We always start with this guy. So we draw a T model. Okay, so that's a T model. So this is your gate. This is your drain. This is your source. Okay, this is 1 over Gm. This is the current source. Gm times VGS. Okay, so this is what you have. Now you look at what is connected to each of the terminal. Let's start from the gate. When you come out of the gate, you see what? Two resistance. That's the biasing resistance. Okay, so and both resistance now are going to be ground, right? Because the top DC is a ground. So these two are going to be ground. So this RG1 and RG2. Okay, these two can be in parallel in the future. And then you see this capacitor CC1, and you can see a resistor, and this is your input. Okay, so that's what is everything is connected to the gate. We got it. So now let's look at what happens at the source. So you can see right away what is connected to source. You have RS, and then you have also CS, and these two can be in parallel. And then at the drain, what do you have? Well, first of all, you see RD, which is connect to ground. Okay, so let's put this RD to ground, and you also have a capacitor, and then with RL, which connect to ground, and then this goes CC2, and then you have your output way over here. So now we got this circuit. And this is very critical for you guys to know how to draw this. And this will be tested again and again and again. So I want to write this in your brain saying, okay, well, this is how we do it. So you got to understand the process and eventually how to draw the actual equivalent circuit. I mean, basically, you start with the three terminals. This is T model. You can draw pi model. Nothing wrong with it, but just it will make you more difficult to solve the problem. This T model is easy in this case. The short for no, because your frequency is so low, it's no longer short circuit. It has impedance. When the frequency is high, yes. Yeah. So in the previous for the future, previous chapters, we always make a short circuit for small signal. That's the middle band. But now we're talking about low frequency band. It's no longer short circuit. Okay. So with this circuit, which is redrawn here for your for your better to understand, we can combine, because when these are together, we can combine, and these two we can combine, and we can also combine a few things like here VGS times GM. We can convert it into ID because that will make it easier instead of using. So this basically you can still use GM times VGS, but since VGS is over here, it's not to ground, so it makes it a little bit more difficult instead. So we're going to do ID. So if you look at the circuit, if you want to take the output, you would have to do a few steps of manipulation. But one thing you can do a couple of things. One is that you can do analytical circuit analysis, by looking loop and node analysis, or you can do, say, a MATLAB, build the circuit, simulate it, or you can write a matrix equation, and then you can solve for it. You can do a lot of stuff to get the answer. But to understand what this result, again, we want to get the inside of this circuit and explain what it means for each of this. And we can break down this circuit into three components or three parts. By doing this, we'll make our life very easy, and then we'll kind of get straightforward the meaning of each of this. So first of all, let's combine these two to get this. And let's combine this two to get RS over CS, okay? And then later on, you can also put this DS in series with 1 over GM, right? So that's what you can do. So we'll make it easier. And then we're gonna also combine like CC2 and RL. However, we cannot really combine because we have to take VO. So what we're doing is we're gonna do it this way. We're gonna mark a few things here. So let's mark it VG over here. This is VG. This is not VGS. Okay, this is VG. And then we're gonna mark ID over here. Yeah. Let me actually erase this, make it a little bit easier. Okay. So this is VG, and this is ID, and this is OVO. And then also we mark this IO over here, just to make it a little bit easier. So we know how do you, our gain will be A is equal to VO over V SIG, which means what we need to do is we get VO as a function of VSIG. So in this case, what we're going to do, we're going to rewrite this equation. The way that we write it is like this. We're going to put VO over VG. And then we put VG, because I'm just trying to mathematically manipulate this equation. So instead of VO over SIG, we're going to put VO over, no, that's wrong, not VO over VG. Let me redo it this way. Try to get my notes here. So what I meant is we're going to get VG over VSIG. So because VSIG here, VG is here, so we get this one. So which means now we are like talking that part circuit. Because now we have VG at the numerator, so somehow we have to put this VG over here by something. And because we need also VO eventually, so we need to put something. So instead, over here, we're going to put we can put ID over here. These are all multiplication. So if we do it this way, we will be able to solve each one of them. This, and this. We can resolve this step by step. For example, in this circuit, how do you get VG? Remember, the current over here is 0. In this case, in the T model, the current going to the gate is still 0, very small. So we neglect this current. If we neglect that current, you can see that VG is this voltage in series with this one, in series with this one. So eventually, you can write VG as a function of VSIG divided by RSIG plus 1 over SCC1 plus this RG. Well, RG is the combination of RG1 and RG2 in parallel. We get this. And then multiply by RG. Because RG is this 2. So if you still have trouble realizing this, I can draw the circuit for you, which means this is circuit here, this RG, this VG, this RSIG, this is CC1, this VSIG. So this equivalent circuit, over here is this. Because the reason we can do it is because the current is 0 over here. So from here, we can now go ahead and convert this into VG over VSIG. So we can convert VG over VSIG equal to this part, right? So it's RG over this. So it's RG over RG plus RSIG plus 1 over SCC1. So that's VG over VSIG. And then we multiply by SCC1 on both bottom and up. We're going to get RG times SCC1 divided by 1 plus RG plus RSIG times SCC1. Okay. Now, remember from the previous little bit beginning at the beginning, what I talked is we always write this into S plus something for low frequency. So we want to get the numerator and the numerator denominator both with S something. So in order to do that, we need to divide the bottom by RG by this, and so we get S. So we get, so bottom get S plus 1 over RG plus RSIG CC1. And the numerator gets S. We divide by CC1, so this RG over RG plus RSIG. So we got this. SCC1, yeah, that's right. So you can see here, again, this is very important. What happens when S is small? Small means this number is much smaller than this. What do you do? Okay, get rid of it. Get rid of it, what's your gain then? For this particular one, the ratio between VG and VSIG. The gain is proportional to frequency. S again is j omega. So which means it increases 20 dB every decade because 1S, 20 log becomes increase. So when S is big, what happens? S much bigger than this one. Then we can get rid of this. We get rid of this S over S equal to 1, and therefore this is your mid-band gain. Okay, that's only between these two. It's not the whole circuit, overall circuit gain. It's only these two. Okay, so now we got this. So next, so if I want to plot this, what do you think it would look like? What do you think it would look like if you plot the body plot or the actual plot, the gain? So there's a point, we have 3 dB. After 3 dB, it becomes constant. Okay, and below 3 dB, what happens? It increases by 20 dB every decade. And what happens when S is 0? Well, this is 0, and this is also 0. When this is 0, what happens? The whole thing is 0, which means there's no VG. VG is 0, apparently the output is going to be 0. Why is that case? What does it mean, S is 0? For what kind of voltage you would have a S equal to 0? DC? Yeah. So if it's DC. So now you go back, you say, oh, for DC, what happens? This is open circuit. This is open circuit. Nothing is converted. So this here is nothing. So it's open circuit. So that's why for DC, the gain is 0. Okay, that's for this. So the next step we're going to derive. I don't have the circuit side by side. I should have that. But the next step, we're going to do this. We're going to look at this ID over VG. So VG is the voltage over here. And we can write down VG because ID comes in over there, and it goes here and here too, right? So we can write VG equal to the total impedance times ID. So that's what we can write. Total impedance of IG. So we can write VG as ID times the total impedance, which is 1 over GM, plus this RS in parallel with 1 over CS. One over C S C little s. So that's what you have. That's the equation over here. So now, which means we can write down ID, because what we wanted to get is we're going to ID over VG, right? So now we can write ID over VG equal to, so ID, we move this aside, we move that to this side. We have 1 over GM plus, so this RS, this in parallel. Parallel means RS times 1 over SCS, RS plus 1 over SCS. So now what we can do is we can multiply GM, and also we can multiply SCS, or we can multiply the whole thing over here. So we get GM divided by 1 plus RS over, we times SCS now. So SCS is gone. So this is SCS. So this is 1 plus RS CS times S, okay? So, and then also this SCS. It's a little bit complicated, but what we can do is we can further take that GM out over here. And we can do this one. We can divide by S, we can multiply, now we can multiply it by this. So we SCS times 1 plus SRS-CS divided by RS plus SCS times 1 plus SRS-CS. So what I'm going to do, I'm going to, no, this is something is not quite right. S plus 1 over GM, move GM here. SCS, no. I got it wrong. There's no SCS here. No, there's no CS here. So, okay. So I did that by mistake. So I'm going to erase this one here. So this 1 plus this. I only multiply GM. So this should be a GM over here. Okay, so there's a GM. So this apparently, I'm going to have to redo this. So it's GM. And now I'm going to multiply this one on top and bottom. So I get the top becomes 1 over SRS-CS divided by 1 plus RS-CS times S plus RS times GM. So we need to write down this to the standard format. It becomes S plus 1 over RS-CS divided by S plus this GM times RS over RS CS. Okay, so we got this. Let me see, make sure this is right. GM times RS. Yeah. So now for this, you already know that you have 1, 0, and 1 pole. So think about it. If S is extremely small, what happens? You can neglect this, and you got only, oh, there's 1 GM here. This GM. So you really get just GM times some stuff over here. But if this S, because there's two values here, so these two values are different, therefore your zero is always like smaller. So in the middle, you can only maybe neglect this one. So S is small, but smaller than this one, but not so small than this one. So you have this. So therefore, your thing will start to increase proportionally. And then when S is very big, you can neglect this one, S over S equal to 1. So this case, you will have your gain curve like this. So initially, you can constant and increase by this, increase by this. And this is your FZ. This is your FL, maybe FP2, like what we call it, FP2. That's how you get it. When S is very small, so this is neglected, you got a constant. But when S is in between these two numbers, this can be neglected, but this cannot be neglected. So you increase linearly by 20 dB per decade. But S is very big. This can be neglected, this can be neglected. SOS equal to 1. Okay, so you get another constant up there. So that's the second portion. And then we can go to our last portion is we want to derive the ratio. I want to go back so that I can see what I want to do is a VO over ID. So we want to get VO over ID. So, okay, so if you look at the VO over ID, which means your ID is over here. You see ID is over there. And your VO is basically CC2 and RL in series, right? So we want to first calculate IO, which basically is in parallel between that. So I'm going to redraw the circuit here, just make it easier. So you have RD, you have this, RL, you have CC2. This is your ID, and this is your VO. So we're going to get this as IO. This is your IO. So we can see that IO is same as here, IO, and same over here is maybe I something, I don't know what we call it, but maybe IX. You can see your ID equal to minus IO plus IX, right? So which means we can get our IO is really just current divider. For current divider, we have to, because the direction is different. You see, one is coming out, one is coming out, so you have to have a negative sign. Or you can say this, IO equal to minus, which is ID over RD plus RL plus 1 over S CC2 times RL plus 1 over S C2. That's your current. That's your current. If we remove the minus sign on this side, we can add the minus sign on this side. So we can get I. Once we get IO, so VO is IO times RL. So now we can get minus ID times all this and times this, and then also times RL. So now we can move ID on this side. So we get VO over ID, which is going to be equal to, I can rewrite all this thing. It's going to be RL times RL plus 1 over S CC2 and divided by RD plus RL plus over S CC2. And we can manipulate this again by some mathematical, for example, multiply SC2 both numerator and denominator. And we can also take this out. So eventually we'll get this expression. Let me show you the expression. It's going to be minus, this is minus sign, don't forget about it. So RL times ID divided by RL plus RD, and then times S over S plus 1 over RL plus RD CC2. So apparently, This has, again, a 0 at 0, which means for DC, the gain is 0, which is perfectly making sense. And for S is small, this can be gone. So your gain increase proportional to frequency. When S is big, this is gone. SOS is 1. So for high frequency, it's linear. But for low frequency, it goes proportional. So if we draw this line, again, it will look like something here. So we call this FP3, and this is your F. This is your gain. Okay, or 20 log. Okay, so we got this. So now you're saying, oh, what happened? You got 3 gains, right? But the 3 gains really, what we have is AV is VO over VSIG. What we break down is VSIG, VG times VG, ID times ID times VO. So now we can plug in all these 3 to get what we wanted. And once we plug in this 3, I just recall the equation here. So just give you minus sign RG plus RSIG. That's the first one. Multiplied by second one is GM times RD in parallel with RL. That's the second one. And then multiplied by S. This is the first one, S plus omega P1 times your S plus omega Z1 plus S plus omega P2, and times the third item is S over S plus omega P3. That's your final combination, because you see your AV is this times this times this. So we plug in everything, we got this equation. And for this equation, so now we see, for low frequency, you have 3 zeros and 3 poles. Okay, and each one of them is, we already draw each one of them is like this, right? So the first one look like this, the second one look like this, and the last one look like this. Of course, the frequency of each of this frequency may be near each other or maybe apart. Who knows? It depends on the parameter selection. But typically, the 3 frequencies are not together. So what you can do is you simply can draw this line is, and we know at high frequency, this is a constant. And that constant is expressed by this part, okay? And then so let me mark down this. This is 20 log AV, and this is your omega or F, whatever you call it. And at the first pole, or omega P2 or P3, for now we can call them like a P3, just to make it easier to understand. But this sometimes might flip. You get 20 dB drop, okay? And then along the second WP2, you get another right? And you get another 40 dB drop. Maybe this way. Maybe draw it like a little flat. Maybe a little flat. Okay. And then you have another drop at omega P1, not drop. But then on here, you have omega Z1 increased by 20 dB. So this is 20 dB for decade, and this is 40 dB, and this is 60, and this is 40. The last 40, because you have a 0, so that 0 will try to erase this to another 20 dB. So this is your low frequency response part. You have 3 poles, 3 zeros. So now you remember, for low frequency response, So how in the future, how do you identify whether it's low or high frequency response? For low frequency response, there's a pole, there's a zero. There's always zero, there's always a pole. So that when S is small, it's an impact. When S is big, you can cancel S on both numerator and denominator. So for low frequency response, there's always equal number of poles and zeros. That'll make it a little easier. For high frequency response, it's interesting because for high frequency response, typically you will have only poles, no zeros. Typically. However, in some situations, you might have a pole. So if you have a pole, what happens? I mean, you might have a zero. So if we're going to draw, okay, so this is actually drawing in a better picture. You have, but in the book, they flip to P2 because they say P2 for due to CS. P2 is due to CS, is always bigger than P3. So that's okay. And this is P1, and this is FZ. So typically, you see that this P2 is due to CSS. This P3 is due to CC2, and P1 is due to CC1, and FZ, of course, is also due to CC1. So that's how it works. And then, so that's your log frequency response. And it's always in the form of S plus omega 0 and S plus omega P. So that's that's a typical, so this omega Z, it could be 0 or non-zero, that's fine. So it can be both. But in any case, you always have S at the numerator and S at the denominator. And you always write it in S plus something. You don't write it in 1 plus something. Okay, you write S plus something. That's for low frequency. But if we go back to common emitter, you see what happens? This is the same, this is the same, that is the same, this is the same, this is the same for the common source. Everything's the same. And you might say, okay, what's the difference? Even the equivalent circuit is the same. Remember the equivalent circuit for the T model? It's like this. So, and the only difference, or maybe two differences, well, you have R pi. And the other difference is that this is not, the current going to the base is not 0. That's the only two difference. So if you do it here, which means this is beta times IB, so this is IB, and this is 1 plus beta times IB. So now you can draw the rest of the circuit. So now you can draw the circuit. Yeah, so there's another one. And then from the output, you have 1 over here, 1 over here. Yeah, we O. And at the emitter, you have this. Oops, you have this. So this circuit is essentially the same as before because this three you can combine. So it doesn't make much difference. RB1, RB2, and R pi can be combined. So this one doesn't make much difference. So the only difference is this 1 plus pi, and this is not 0. If you think beta is very big, these two circuits is almost identical except R pi is combined into RB1 and RB2. But if you think RB is not 0, you can still consider it. You can get a gain which is a function of beta. That's all. That's all you have. So we're not going to go to this one in detail, but this is what I meant. The equivalent circuit you can do. Well, in this one, actually, I'm sorry. I made a mistake. There's no R pi. Because we're doing this, we're doing this T model. So there's really no R pi. If we get the pi model, would have been a pi. Okay, because this becomes this RE. We have to go to this RE. Okay, so now you have this model. You can solve for the circuit again. You can do all the derivations. You'll have 3 poles. And eventually it will come out, the 3 ports are essentially similar to the MOSFET. Okay, so this is almost the same. So now let's look at, maybe I'll go back to this slide, but I want to come this here first. So for the frequency response, if we go draw the whole thing, now we have this. We have, okay, so we have either omega or F. And then for the low frequency, we have 40 dB, 60 dB, 40 dB, 20 dB, and then here. And we have one pole, one pole, one pole, and 1 0. So this is FZ, this is FP1, FP3, FP2. And in the middle band, you might have something like this. Depends on what you have. So this omega H1, omega H2, and then maybe here is omega Z2. You can use omega F either way. It doesn't really make a huge difference. So this is your overall frequency response. And the middle band here is what we call a middle band. So in the middle band, the gain is a constant. It has a frequency, doesn't do anything to it. But once you're close to this 3 dB, once you get to this like a 3 dB over here, which is right here, all this 3 dB over here, your output is going to start to distort. And once you go beyond the 3 dB, your gain is going to drop significantly. On the output side, it's going to do the same thing, the low end and the high end. And eventually, so for the low frequency, you always have S plus omega Z, S plus omega P. And for this, you always have 1 plus S over omega H and 1. So this is your high frequency. But if you do have a 0, this can become like a 1 plus S over omega Z, 1 plus S over omega H. So this is like this one. So high frequency, low frequency. So this one, if omega Z is 0, you can do it like this. So this is low frequency and high frequency. So you can see that for the low frequency, you always have a 0. It doesn't matter whether omega Z is 0 or not. You always have a 0, which means there's always S at the numerator, and there's S plus something at the denominator. That's for the low frequency. For high frequency, you can have either 1 over S plus S over omega H, or you can have 1 plus S over omega Z divided by 1 plus S omega H. So the idea, the way that it's written, is to make sure you can have the denominator and the numerator and denominator becomes 1 in the middle band, regardless. Okay, so this is how you do it. So now in the sense that these ones is dependent on the device. So when you design your amplifier, you need to determine what is your high frequency that you want to reach. Your frequency is very high, you might have to go to find a device that is more, these ones are higher. Those devices are generally more expensive. Okay, but if you your frequency is low, you don't have to worry about it. You can pretty much pick any device or even just load the device. The device difference, the price difference can go from anywhere like 1 cent, I mean, on a quantity, or on DGK, you can buy 20 cents for the device, load the device, or you can spend $200 to buy a single device for very high-end application, for military application, for example. Very high common mode rejection ratio and very high frequency in the gigahertz range. So that's the high frequency part. It's basically device dependent. The low frequency part, you have a control because you can select CC1, CC2, and CS. You wanna your frequency value go to lower? Okay, just choose a larger capacitor. Choose a larger capacitor. But of course, you might already know, okay, larger capacitor means larger size, higher cost. Do you want really to do that, right? So there's a design trade-off. That's why when you design this amplifier, you have to understand your application. If your application frequency is not that low, forget about large capacitance. I can choose a small capacitance. I still get what I want. But if your frequency goes really to the say hertz or 0 point sub, unit hertz, you might have to design these capacitors huge devices. Okay, so that's the kind of thing that you need to do. And then so this basically already covered how do you select CS and CC1 and CC2. So this are very important to you to design. Okay, I already discussed the way that this is written. So basically, S plus omega Z over S plus omega P, or this is 1 over S plus omega H. No, I mean, same thing, I make a mistake. So this is, I'm going to just rewrite it so that 1 over 1 plus S over omega H, or 1 plus S over omega Z plus 1 plus S over omega H. And this one can be written as S over S plus omega P. So you gotta really just 4 different ways to express it, okay? I think with that, we're done with today's lecture. Any questions? Are you guys eager to take the exam, huh? Okay, well, you'll have it. So today's password is Moonlight with M and L both capital. So it's Moonlight. Try if you can access it. Moonlight. Yeah. Capital L and a capital